welcome to the class today. My name is Negedu Godwin and I'm your regular anchor. So today we're going to be looking at range equation, wave interference, decibel and TGC. I want to extend my appreciation to these wonderful people who have contributed greatly to my knowledge. So, range equation, what is it all about? You see, the ultrasound system operates on the pulse echo principle, and to calculate the depth of each echo or depth of each reflector, the system uses the range equation. And of course, the range equation is distance equals to time times velocity of sound divided by 2. So since we know the velocity of sound in soft tissue to be a constant of 1.54 millimeter per microsecond, we can derive distance to be t times 0.77 microsecond. So this is basically the range equation that is used to calculate the distance or the depth of the reflector, and this is what you have: reflector distance in mm, which is equals to 1.54 millimeter per microsecond times the goal return time in microsecond. So from the above equation, we can deduce the following. Distance is proportional to goal return time. Deep echoes, we have long goal return time. Superficial echoes, we have short goal return time. Now, in the range equation, the velocity of sound of tissue, which is 1.54, is programmed into the machine and it does not change. So it's actually the assumption on which the machine is built on. It is called the calibration speed of the ultrasound equipment. The basic assumption in ultrasound is that the velocity in the medium, that is the soft tissue now, will match the calibration speed. This is true in majority of the time, but occasionally the velocity in medium does not match the calibration speed, and this will result in velocity of sound error, resulting in issues like misregistration of interface, which we will call velocity artifact or propagation speed artifact. And when these are present, it will also help to identify certain lesions like lipoma, angiolipoma. So that misregistration error based on that assumption is not all bad. What is for the sonographer to know how to use it. In soft tissue, sound will travel to and fro from a depth of 1 centimeter in 13 millionths of a second. That is 13 microsecond per centimeter. That's to say, when the pulse time of flight is known, then the distance to a reflector can be extrapolated. Now this table shows us the goal return time on distance or depth of the reflector. So in soft tissue, like we just said, every 1 centimeter, the goal return time is 13 microsecond. In every 2 centimeter is 26 microsecond. Every 5 centimeter is 65 microsecond. And every 206 microsecond is 20 centimeter distance covered. Now, what is the concept behind wave interference? When 2 or more waves arrive at the same location at the same time, they will interact to form a new wave, and this is called wave interference or wave interaction. Now, the resultant wave may have a different amplitude or frequency depending on the amplitude, frequency, and the phase of the original waves. Wave interference affects beam formation used in electronic beam steering, electronic focusing, Doppler instrument, and transducer matching layer design. Now, an acoustic wave is a repetitive cyclical variation of acoustic variables. So one complete cycle is divided into 360 degree. So the cycle begins at 0 degree and ends at 360 degree. The constant of phase is useful to describe the relationship between two or more waves. Waves which superimpose may be either in phase or out phase when they superimpose. In phase means the peak and the valleys of the two waves are aligned with each other. They are 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees position coincides. So they align. Now, if two waves superimposed in phase, in other words, they align, the energy in the wave will be additive, and the resultant wave will have a greater amplitude. Now, this type of positive wave superposition is known as constructive wave interference. Whereas in out phase, if two waves superimpose out of phase, their peaks and valleys does not align. Yeah, the result is not a net. The result is a net loss of energy in the resultant wave. Now, this type of negative superimposition is destructive wave interference. Now, decibel units. We've dealt with decibel units in other lectures, but here we'll look at it briefly. The decibel scale is very useful tool in physics. It can be used to express changes in many physical properties, including sound intensity, power, and amplitude, as well as voltage, gain, attenuation, and dynamic range. The decibel scale is known as a relative scale. This means that it's used to measure a change in the physical property. The decibel is used to express a change in two values with the same unit. For example, we could express a change in sound intensity from 4 milliwatts per second square to 60 milliwatts per second square as a decibel change. This decibel scale is a way of expressing a ratio of two values. When using decibels, it is helpful to determine the ratio first and then convert the ratio to decibels. The decibel scale is a logarithmic scale, and the logarithmic scale used in logarithm of quantity, and is very useful for data that covers a wide range of value. The decibel scale is 1/10 of the Bell scale, and of course, that is named after Alexander Graham Bell. The decibel scale equation. To use the decibel scale, we need to know the decibel equation. There are two decibel equations that we need to know. One is used to deal with ratios of intensity or ratios of power. The other is used to deal with ratios of amplitude or ratios of voltage. Decibel equation for ratios of intensity or power is 10 log ratio equation. That is, decibel is equals to 10 log ratio. Now, this is known as the 10 log equation. If the question deals with intensity or power, we'll use this equation. For example, you want to express a change in power from 10 milliwatt to 100,000 milliwatt in decibels. To solve that problem, you may want to follow this step. First, use the correct equation. Yeah, and of course, you know the correct equation here will be the 10 log equation. Then you create the ratio. So you make sure first that they're in the same unit. Here in the question, both are in milliwatts. So always place the starting value on the bottom. Yeah, that's the original value in the bottom. And in this case, the ratio will be 10,000 divided by 10. Yeah. Simplify the ratio here. It will be the ratio will be 100,000 divided by 10. So to simplify it, it will be 10,000 to 1 ratio. Yeah. Now apply the 10 log equation, and the 10 log equation is dB, that's decibel, equals to 10 log 10,000, and log of 10,000 is equals to 4. That's to say, dB is equals to 10 times 4, and 10 times 4 is 40. That is the 40 decibels. That answers the question that deals with intensity of power. So you use intensity of power, you use the 10 log equation. Now, a change in power from 10 milliwatts to 100,000 milliwatts expressed in decibels is 40 decibel change. There's also a decibel equation for ratio of amplitude or voltage, and it is decibels equals to 20 log ratio. This is known as the 20 log equation, and is used to express ratio of amplitude or voltages. For example, as in the first case, you want to express a change in amplitude from 100 pascals to 10,000 pascals in decibels. So to solve this problem, you follow this step. Use the correct equation. Well, in this case, you know you are dealing with pascals, that is amplitude. So you use the 20 log equation. You create a ratio. First, you also need to identify that they are in the same units. Since they are in Pascal on both cases, always place the starting value on the bottom. In this case, 10,000 will be divided by 100. To simplify the ratio, it will be 100 ratio 1. So when you apply the log equation, the decibels will be equals to 20 log 100, and log 100 is equals to 2. Decibel therefore will be equals to 20 times 2, and the decibel the final answer, the change, will be 40 decibels. So a change in amplitude from 100 Pascal to 10,000 Pascal will be expressed in the decibel as 40 decibel change. And as usual, we talk about time gain compensation. We will not stop talking about it because it is relevant for image optimization. So, time gain compensation makes all the echoes arising from similar structures appear the same brightness, regardless of the depth of the reflector. It is also called depth gain compensation, or swept gain compensation, or distance attenuation compensation. Let's look at the objectives and the obstacles for TGC setting. The basic objective is to display identical reflector to appear similar regardless of the depths. But the obstacles, identical reflectors produce different echoes when they are located at different depths. The go-return distance that the pulse travel is different for identical reflectors at different depths. The shorter the path, the less the attenuation, and it shows stronger reflection. That will be it will be brighter on the display you have a brighter image on the display when the path is short. The longer the path, you have more attenuation and it shows weaker reflections, and that's to say there will be darker image display. So how do we solve the problem? And that's the whole idea behind time gain compensation. Time gain compensation makes all echoes arising from similar structures appear at the same brightness regardless of the depth of the reflector. The components of time gain compensation curve includes a near gain, display control, slope, near and far gain. Let's look at them one after the other. Near gain is the minimum amplification level. It adjusts the amplification of echoes in the near field that is nearest to the transducer. If the near gain is set too high, the image will appear too bright. If the near gain is set too low, the image will appear not filled in enough in the near field. The second level is the delay control, and that regulates the depths at which the compensation begins. Echoes from shallow depths do not need extra amplification or compensation. It allows the operator to delay the start of the amplification process. Delay control can be helpful when there is a large amount of subcutaneous fat that does not need to be imaged. The control can be set such that the amplification process will start past the fat level with no echoes being amplified before that point. However, the delay control must be set carefully so as not to exclude any amount of superficial structures from the image. The next level of TGC is a slope. Now in this range, extra amplification is applied for ever increasing depths. Slope rate of the TGC curve is the rate of compensation which is being applied to the image in decibels per centimeter. The next level is the knee. The knee is the end point on the slope. It is a point of maximum or greatest compensation. Remember, compensation is amplification, yeah? That's applied to the returning echo. Now, this value is usually set at the most posterior aspect of the structure to be imaged. For example, in imaging the right lobe of the liver and the diaphragm, the knee would be set at the level of the diaphragm. Then the far gain is the maximum amount of amplification level that any echo within the image can be amplified. This will apply to most posterior tissues. Now, resetting the TGC curve, set the knee to the back wall of the structure. Yeah? The structure to be evaluated. Set the knee to the back wall. That is the diaphragm is when you're doing a liver scan. Adjust the near gain, adjust the far gain, adjust the overall gain, adjust the delay if necessary, especially when you have a large patient that have large subcutaneous fat. Change the transducer frequency for penetration where it's necessary. So without TGC, the image would have a light to dark gradient from the near field to the far field. In other words, the near field will be brighter, the far field will be dark. TGC will help to compensate for the loss of ultrasound waves in the far field by amplifying their signals. The result is an even brightness in the entire field of view. This image is an example of TGC setting with respect to the image on the screen. Here on the left, you have TGC is too low in the far field. That's why the whole area is dark, it's black. While the middle image shows TGC too high in the near field. So we're going to have it very bright. And when it's very bright, images are obscured. And the right image is a corrected TGC that makes a uniform appearance of the structure across the screen from the top to the bottom part of the screen. And this is the image of the knobs, the TGC knobs. It can be adjusted via a number of these slides you see, and they correspond to specific depths within the patient, like we've just discussed. So generally, people say you adjust it to have a banana shape, yeah. But it's always important because there is no, depending on the patient and structure and transducer frequency we are using, you every time have to make adjustments to optimize your image. For example, this image on the left, the TGC controller in neutral position. So superficial structures like thyroid tissue, thyroid TGC controller plays in neutral, yeah, because it's a very small field of view that you require. So you may not necessarily do a far end, just adjust your depth and select the right probe. Then here, TGC control adjusted per depth for deeper structures in the abdominal structure. So you can also notice how that the upper keys are below the neutral line, and the lower, and it keeps increasing as you go below. Why? Because you are compensating for the loss of echoes as the sound pass through the whole depths. I want to thank you for joining this lecture. Please like, share, and subscribe. You can also put on the notification to receive all our free lectures. For more information about our paid classes, please send an email to sonoeyesdiagnostics@gmail.com or WhatsApp me at +234 9019 144 175, or you can visit our online store at sonoeyes.business.site or ambanek.business.site. Attempt the quiz in the description and leave me a comment. Until the next time when I come your way again, keep learning.